So let's talk about standing waves again. Primarily, what does a standing wave look like? So if I have two fixed ends, I want the simplest standing wave is going to have just those two nodes because they're fixed. Fixed means that it's not vibrating up and down. I have two fixed nodes, and the simplest standing wave basically is going to look like this. I've got my two nodes here, and I got a giant anti-node here. If you looked at the previous video that I made with a vibrating string, that was not the simplest one. So this is the first, what's called the first harmonic. Now, the second simplest, and so when I'm looking at that, well, let's think about what a wave is. A full wave is basically, you go up and down, or you might go down and up, but there's some combination of up and down, and you end up back where you start. Well, this is basically, I'm going up, and I'm back to where I started. There is no dip down below. And so this right here is a half a wavelength. So I've got 1/2 of a wavelength. Whatever that distance is, if this distance here is L, then L is equal to a half a wavelength. Now that's the first harmonic. Second harmonic, that's just the language that's used. The second harmonic, basically, I'm going to have, well, that has two nodes. This next one has three nodes. And so the next harmonic, got a node here, here, and here. This is the second harmonic. And notice that, and again, this is representing, this is the string. It's vibrating up and down right here. And it's vibrating so fast, as in the example that we did before with the string, it's vibrating so fast that you really can't tell if it's up here or down here at any particular time. But basically, it's the string vibrating up and down from the standing wave. I got waves coming this way, the reflection's coming back, there's interference, destructive interference, complete destructive interference at the node, complete constructive at the antinode. And what we have here is basically, that's a full wavelength right here. So the wavelength is equal to whatever the distance between those outer nodes is. The next harmonic, well, I have two nodes here, three nodes here, I have four nodes here. So let's see. That's basically what the next harmonic was going to look like. Boom, 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 boom. Those are my four nodes. Notice there's one wavelength right there, but then I got an extra one right there. So this is, I now have 1.5 or 3/2 of a wavelength is equal to the length between those two things. And so on. So there's a progression here. Go from a half wavelength to a wavelength to the next wavelength for the first harmonic, second harmonic, third harmonic. Now, in the one that I did, the example I did, sort of written over here, I had 5 nodes. And so that's going to be, well, the fourth harmonic, because that had 4 nodes right there. I'm going to erase this top one right here so we can actually do the analysis. Again, the length between them is L, and I measured that for this particular one. Ding, ding. All right, so that's basically what the vibrating string looked like. From what I showed you is we were looking at this node right here, and I think we looked at that node, but 1, 2, 3, 4, 5 nodes. 4 antinodes. This is the fourth harmonic. It's the fourth simplest standing wave that I can create. And so I've got 1, 2. I have 2 complete waves here. 2 complete waves. There's the first complete wave right there, and the second complete wave is from here to here. And so I have 2 complete wavelengths in that one length. And so the question is, what is the wavelength here? Well, the wavelength. I measured the distance from the nodes to the nodes, and I'm pointing to where the objects were. I measured this distance on the string. That's from the tip of the vibrating string. That's from this point right here to the top of the pulley, because that was the other node. So this, actually from the way this was right here, this was the attachment to the string vibrator. And this right here was the top of the pulley. And so that distance right there, I measured out, is 1.01 meters. And so the wavelength was, well, just divide by 2, divide by 2, divide by 2. The wavelength of that particular wave was, to do some fancy math here, 505, or 0.505 meters, just a little bit more than a half a meter. Now, what was the tension in the string? Well, the tension in the string, let's give myself some room here. The tension in the string is, basically it was the weight hanging off the end. Well, the weight hanging off the end was just, that's the weight hanging off the end. Very similar to the centripetal force lab that was done. The weight hanging off here, and the mass I had was 70 grams, 0.07, and let me just double check that. That was a 50 gram mass and a 20 gram mass, so 70 grams, so 0.070 kilograms times 9.8 meters per second squared. And that ends up being 0.6 So I did my math right, 0.686 newtons. So my speed of my wave. Now, in the lab that you do, you're going to be finding a whole lot of wavelengths and tensions here. You're going to be doing a plot and using the slope. I'm just going to do a quick analysis here with just this one sample. Usually with one sample, whatever errors are in there are usually accentuated, or might get lucky and actually get the right answer. But the whole reason of doing a whole lot of trials and looking at the slope is figuring that you're just as apt to be too high in one case as too low in another case. And so all the errors sort of cancel each other out. But in this case, let's take a chance. Let's find out. Take chances, make mistakes, get messy. So I know that the speed of the wave is equal to the tension. There's one other piece of information I need to know. I need to know the linear density. So I'm going to stop it here, get the linear density, and the next video we'll finish doing the analysis.